Bro, Mars literally broke itself. Number 13. Borealis Basin. 40% of Mars sits lower than the rest. The entire northern hemisphere drops kilometers below the battered southern highlands, and the boundary between them is one of the sharpest geological divides in the solar system. In 2008, a team led by Jeffrey Andrews Hanna at MIT used gravity data from Mars Reconnaissance Orbiter to trace buried ring structures beneath those smooth northern plains. The rings matched what a colossal impact basin would leave behind. Their model pointed to a single oblique strike by a body roughly 1,900 kilometers across, something larger than Pluto's Mooncairn, slamming into early Mars at a shallow angle. Other researchers disagree. Some argue multiple impacts built the lowland over time. Others say deep mantle convection could produce the same shape without any external strike at all. The data fits pieces of each idea, and none of them completely. What nobody disputes is the basin itself. Crater counts on the floor read younger than the southern highlands, which means something resurfaced that ground after it formed. If a single impact did this, the energy released would have been enough to boil oceans and send shock waves through the entire mantle. 40% of the planet gone flat. Number 12. Hellas Planitia. Drop the full height of Mount Everest below the Martian surface and keep digging for another 2,000 meters. That is how deep Hellas goes in places. Over 7 kilometers below datum, making it the deepest confirmed impact basin in the solar system. The European Space Agency's Mars Express spacecraft mapped the rim and found benches that resemble ancient shorelines. Omega, its mineralogy instrument, picked up clay-rich layers and hydrated salts inside the basin. Those minerals only form when water sits on rock long enough to alter its chemistry. Deltas and layered fans suggest rivers once poured into this hollow, and some thermal models estimate the post-impact lake could have reached 5 kilometers deep. The strike itself dates to roughly 3.9 billion years ago during the late heavy bombardment. An impactor that large would have flash-boiled subsurface ice across a wide radius, launched steam and dust into the upper atmosphere, and shifted climate patterns for millions of years afterward. The strange banded terrain on the basin floor looks like hardened slurries. Material that was liquid, superheated, and then froze in place. Researchers still argue about whether Hellas alone could have stripped enough atmosphere to change the planet permanently. The answer probably depends on what the atmosphere looked like before the hit, and nobody has settled that question yet. Number 11. Valles Marineris. Mariner 9 arrived at Mars in 1971 and sent back the first clear images of a crack that runs a quarter of the way around the planet. The canyon system stretches 4,000 kilometers, roughly the distance from New York to Los Angeles, and plunges up to 7 kilometers deep. The Grand Canyon would vanish inside one of its side tributaries. Most planetary scientists tie its origin to the Tharsis volcanic rise. As that massive bulge pushed upward, the surrounding crust stretched and fractured. Enormous blocks of rock dropped along fault lines, and gravity pulled them deeper over time. High-rise images from Mars Reconnaissance Orbiter show individual landslide deposits where boulders the size of city blocks tumbled into lower valleys and buried everything beneath them. The exposed canyon walls give geologists direct access to layered crust that would otherwise sit hidden kilometers underground. CRISM, the spectrometer aboard MRO, found sulfate and clay minerals in those layers. Signatures of water interacting with rock at different depths and different times. The canyon did not open gently. Some collapse zones show evidence of catastrophic failure, entire cliff faces breaking free in single events rather than eroding grain by grain over millennia. Whatever drove the Tharsis rise upward, it tore this wound open fast enough to leave the raw edges still visible 4 billion years later. Number 10. Casse Valles. Imagine a river channel wide enough to swallow a small country. Casse Valles is the largest outflow system on Mars, stretching over 3,000 kilometers with channel widths that exceed 400 kilometers in places. Streamlined islands, scoured bedrock, and giant terraces record something that moved far faster than any river on Earth. The leading explanation is catastrophic release, groundwater or melted subsurface ice escaping in sudden massive pulses. Victor Baker at the University of Arizona has spent decades studying these channels and estimates peak discharges that dwarf the largest known floods on Earth by orders of magnitude. Some flows gouged meters of bedrock in single events and rolled boulders the size of houses downstream. Multiple terrace levels show this did not happen once. The floods came in waves, possibly triggered by volcanic intrusions heating subsurface ice or by impacts that cracked the crust and released pressurized aquifers. Each pulse stripped soil, exposed deeper rock, and dumped sediment into downstream basins where it hardened into layered deposits. The braided channels and scoured islands are still sharp. Whatever carved them did so with enough force to leave marks that 4 billion years of wind erosion could not erase. Number 9. Megatsunami shorelines. In 2016, Alexis Rodriguez and colleagues published evidence for 2 separate megatsunamis that struck the ancient northern coastline roughly 3.4 billion years ago. The trigger for each was a large impact into a shallow northern ocean. One of those strikes left an impact scar about 120 kilometers across. The resulting waves reached hundreds of meters high and surged inland, dragging boulders, ripping sediment from the seafloor, and carving backwash channels in directions that make no sense for normal river flow. The deposits they left behind are not beaches. They are hummocky fields of broken rock and mixed debris, what planetary scientists call thumbprint terrain, stretching for hundreds of kilometers along the suspected ancient shore. Between the 2 tsunami events, the climate cooled enough for the second wave to freeze as it advanced, leaving lobes of ice-rich debris instead of liquid runoff. That frozen signature is what allowed Rodriguez's team to distinguish 2 separate strikes rather than one. If Mars had oceans, these shorelines are the clearest record of what happened when something large hit the water. The coastline did not erode, it was demolished. Number 8. Secondary crater chains. A single large impact does not end at the rim. The blast throws out chunks of rock at high velocity, and those fragments arc across the sky and slam back into the surface, each one punching its own smaller crater. They land in lines and clusters that point back to the original strike like arrows on a map. On Mars, the Themis instrument aboard Mars Odyssey has mapped chains of secondary craters stretching hundreds of kilometers from parent basins. Elongated pits indicate debris that hit at shallow angles. Tight clusters mark fragments that landed nearly simultaneously. A single primary impact can scatter thousands of secondary projectiles and pepper the surface across an area larger than Western Europe. The practical problem is that secondaries confuse crater counting, which is the primary tool scientists use to date Martian surfaces. A plain littered with secondaries can appear millions of years older than it really is because each tiny pit mimics an independent impact. Bill Hartman, one of the pioneers of crater age dating, has cautioned that secondary contamination may have skewed age estimates across large swaths of the planet. One strike. Thousands of scars, and every age estimate in the blast zone becomes suspect. Number 7. Lobat ejecta. Around many Martian craters, the ejected material did not fall as a thin curtain of dust. Instead, it flowed outward in thick, rounded lobes, pancake-shaped deposits that froze in place with blunt, raised edges. The mechanism is straightforward. When an impactor hits ground that contains ice or wet sediment, the blast melts that frozen material and turns the debris into a fast-moving slurry. The flow hugs the ground, rides over obstacles, and buries the surrounding terrain under meters of hot, chemically altered mud. Pete Schultz at Brown University has run laboratory impact experiments that reproduce these lobate patterns and confirmed they require subsurface volatiles to form. That means every lobate ejecta blanket is a frozen record of where ice or water was hiding near the surface at the moment of impact. The lobes also carry heat far beyond the crater rim. Where they settle, they bake the underlying rock for centuries and create layers of high-temperature minerals that orbital spectrometers like CRISM can spot from orbit. The catch is that lobate flows also destroy evidence. They bury older terrain, ancient riverbeds, earlier crater floors, whatever was there before, under a thick blanket of blast debris. Each new impact erases the record of what came before it while writing its own. Number 6. Recent impact craters. Between 2006 and 2012, the HiRISE camera aboard Mars Reconnaissance Orbiter caught something extraordinary. Fresh craters appearing on surfaces that had been imaged just months or years earlier. The planet was being hit in real time. Some of the new craters measured about 150 meters across and threw bright ejecta as far as 14 kilometers. In several cases, the blast punched through surface dust and exposed clean water ice underneath. White patches surrounded by dark debris, sharp and fresh against the ancient plains. These live impacts let researchers test models against actual events rather than ancient scars. They can measure shock effects, watch how ejecta interacts with ice, and track how quickly wind begins to soften the crater edges. Ingrid Daubar, who led much of this work at JPL, has cataloged hundreds of new impacts and used them to refine estimates of current bombardment rates. The finding confirms something that the ancient record already suggested. Mars is still being struck, and even a modest impact leaves a mark that orbital cameras can spot within weeks. The bombardment that scarred this planet billions of years ago never fully stopped. It just slowed down. Number 5. Cerberus Fossae. 1,200 kilometers of near-vertical fissures cut across the Elysium Planitia region. In places, the walls drop more than 500 meters, slicing through volcanic plains like surgical incisions that never healed. The fractures opened when subsurface magma pushed the crust upward and then pulled it apart, creating parallel grabens that served as conduits for both lava and water. The volcanic deposits lining these cracks are among the youngest on Mars. Studies published by David Horvath and colleagues in 2021 identified a dark pyroclastic deposit near one of the fissures and dated it to as recently as 50,000 years ago. On a planet supposedly dead, that is yesterday. Then came InSight. NASA's seismometer, sitting on the surface roughly 1,600 kilometers away, recorded repeated Marsquakes originating from Cerberus fossae. Magnitudes ranged between 2.8 and 3.8. The low-frequency events came from depths of 15 to 50 kilometers, consistent with a warm, structurally weakened zone where magma is still moving beneath the surface. Orbital imagery shows fresh rockfalls and dislodged boulders along the fissure walls, evidence that the shaking is ongoing. Cerberus fossae may be the youngest active wound on the planet, a crack that is still widening while everything else slowly weathers shut. Number 4, Argyre Basin. The second deepest impact basin on Mars sits in the southern highlands. A round depression roughly 1,800 kilometers across and 5 kilometers deep. Only Hellas, the scar covered earlier, goes deeper. The impactor that carved Argyre was estimated at around 200 kilometers in diameter. It struck during the Noachian period, between 3.9 and 4.1 billion years ago, close in time to the bombardment that created Hellas. The blast left concentric rings of rugged mountains, the Chiritum and Nereidum Montes, radiating outward from the rim like ripples frozen in stone. Inside the basin, channels like Ouzboy Vallis record water flowing into and out of the hollow. Glacial landforms, including eskers, moraines, and drumlin-like ridges, suggest thick ice sheets filled the floor at some point after the impact. Gravity data from Mars Global Surveyor shows a mass concentration beneath the basin where dense volcanic material flooded the depression and caused the crust to sag under the load. Argyre captures what happened after the initial blow. Water pooled, ice advanced, volcanoes filled the wound with lava, and the crust bent under the weight. 4 stages of destruction layered on top of each other, each one overwriting the last. Number 3, Tharsis Fracture Complex. The largest volcanic province in the solar system did not just build Mars up, it tore the planet open. The Tharsis Rise covers an area roughly the size of North America and stands 5 kilometers above the surrounding terrain. Its weight flexed the lithosphere, opened radial faults, and created graben systems that extend thousands of kilometers in every direction. Valles Marineris, the canyon covered earlier, likely owes much of its depth to Tharsis-driven extension, but the damage goes far beyond one canyon. Noctis Labyrinthus, a maze of collapsed valleys at the eastern edge of Tharsis, formed when the crust stretched so thin that blocks the size of neighborhoods simply dropped into voids left by retreating magma or sublimating ice. The fractures acted as pressure valves. Heat and volcanic gas escaped along them, weakening the crust further and making it more vulnerable to impacts. Eruptions along the Tharsis Shield volcanoes buried older surfaces under successive lava flows, erasing whatever record had existed before. Repeated cycles of eruption, fracture, and collapse rewrote the geology of a quarter of the planet. The damage was not sudden. It accumulated over hundreds of millions of years, each eruption and each fault adding another crack to a shell that was already compromised. By the time Tharsis finished growing, the surrounding crust was laced with fractures that would never close. Number 2, Jezero Crater. 2 river channels converge on a 49-kilometer wide bowl in the Nili Fossae region. Where they entered, they built a fan delta, layered sediment stacked in clear horizontal beds, visible from orbit, that record a lake which lasted long enough to leave a geological signature. CRISM data from Mars Reconnaissance Orbiter identified smectite clays in those delta layers. Smectite forms when basaltic rock sits in near-neutral pH water for extended periods. That mineralogy is what ultimately drove NASA to land Perseverance there in February 2021. The rover has since drilled and cached rock cores from the delta front. Images show alternating fine-grained and coarse layers, cycles of calm deposition followed by flood pulses that washed coarser material into the lake. Rounded pebbles embedded in some layers confirm sustained water flow, not a single flash event. Whether that lake ever hosted life remains genuinely unknown. The chemistry is permissive. Clay minerals can shield organic molecules from radiation, and the water conditions look habitable by Earth standards. But permissive is not proof. The cached samples, if they ever reach an Earth laboratory, may answer the question. For now, Jezero is the clearest single record of what Mars could have been before it lost its water, its air, and its chance. Number 1. Olympus Mons. The tallest volcano in the solar system rises 22 kilometers above the surrounding plains, but its most dramatic scars are not at the summit. They ring the base. Massive sheets of crust, called aureole deposits, peeled away from the flanks and slid hundreds of kilometers outward in catastrophic landslides that rank among the largest mass-wasting events known on any planet. The basal scarp, the cliff that marks where the volcano's edge meets the surrounding plain, drops 6 to 8 kilometers in places. That is a vertical wall taller than any mountain range on Earth, and the material that once stood there is now spread across the lowlands in folded ridges and chaotic rubble fields. James Head at Brown University and colleagues have modeled these collapses and found that gravitational instability from the volcano's own mass, combined with possible ice layers beneath the flanks, could trigger failures that moved entire provinces of rock in single events. Some models add seismic shaking from nearby impacts as a secondary trigger. The aureole deposits buried older landscapes and created fresh, chaotic terrain that later impacts cratered on top of. Olympus Mons did not just build itself. It shed enormous pieces of itself across the surrounding plains, and those shed pieces became new scars layered over whatever was there before.